It's been a long weekend and I need a bit of a review. Except that, all right. So, first, let's just do a brief run through. Those look all familiar to you guys? You can name them all. You remember how they're related? We know that these are kind of related by the radius to the linear variables. So we're, in that case, talking about how far an object might travel should it be on a platform that's spinning. So if I have a, something like this that's spinning, we're talking about how that point on the edge, it might be moving both in linear fashion and in angular fashion. Which brings up also the concept that that one little piece could be also experiencing a radial acceleration. The radial acceleration is also known as a centripetal acceleration. And it's related to how fast it's going. All of that and the motion equations that go with it, we call kinematics. So when I say we've talked about rotational kinematics, that's what I mean. So outside of that, getting into the not what is happening, but why things are happening, we talked about the difference between linear kinetic energy and rotational kinetic energy. We talked about that, I guess, a little bit on Thursday. So taking the same object that's rotating, a single point on the object has kinetic energy equal to 1/2 mv squared, while if the whole object is rotating, we can sum that up to this concept of 1/2 I omega squared. Both of these still deal with the inertia of the object. This is the inertia of an object that's center of mass is changing location. I'm going to say it just like that, so that in your notes you kind of make that clear. This object's moving from one place to another, and therefore its kinetic energy is based on taking its entire mass and moving it from one place to another. So to use this one, the object has to change location. Okay, so object changes location. This one is for objects that are rotating. So it could be staying in place but spinning. I'm going to put could be staying in place. It is perfectly acceptable to have an object that does both. That both is spinning and changing location. If it was doing both, you'd have to look at both. With the last little piece here, that I is the moment of inertia. We talked about moments of inertia too. So let's take a few seconds to talk about moment of inertia. The moment of inertia would be better phrased as rotational inertia. This is how difficult it is to twist or turn an object. It's how difficult it is to twist or turn an object. We know that it's based on how spread out the mass is. The most important takeaway, the thing that should make it to a note card, is that the farther away the mass is from the axis of rotation, the harder it is to turn the object. Now, this led us to a discussion of how you would actually calculate the moment of inertia. And for that, we talked just a little bit about it. Said that generally the definition of moment of inertia mathematically is to add up every piece of the object's mass and how far away it is from the axis squared. That r part being squared, it's more important. This is technically the definition of moment of inertia. But this is also what we call the point mass definition. So really this is like a fake definition. We don't really use this. It means that if you have like a bunch of individual pieces of an object and you were going to take the whole thing and cause them all to spin, then you would take each piece. It's not real. We use it for mathematical purposes, but it's not really an object's moment of inertia. Real objects are smooth or rigid. And for rigid objects, we use a little calculus. We can come up with expressions for the moment of inertia for different objects based on their shape and their size. There are a bunch in your textbook, a table of them actually. But there's just a few of them that I think you should keep in mind. Like a bar rotated about its end. It has a moment of inertia of 1/3 ml squared, where L represents the length of the bar. You would not be required to memorize these. You might be required to recognize these. And one of the things that I would encourage you to consider for your recognition is be able to recognize from maybe a picture which object should have the larger moment of inertia. Remember, it's about how far away from the center of rotation the mass is. So one of the things I tried to emphasize on Friday is that if I take the same bar and rotate it about its middle, then I would expect the moment of inertia to be less because the mass isn't as far away. That's what I mean by recognition, that the lower object, the bar about its center, should have a lower moment of inertia than the bar about its end. I could see me having 3 or 4 objects, a picture of them, and you rank them from the smallest moment of inertia to the largest moment of inertia. It might even be a single object, and I show several different axes through it, and you do the same thing. So I expect this moment of inertia to be less because the mass isn't as far away from the axis of rotation. And it is less. It's a quarter of the actual value. Same size bar, rotate it through its center is a little easier. And then right as the bell started to close, I suggested you take a look at the table for a couple of other shapes. A ring, a disc, a hollow ball, and a solid ball. These are all objects I figured you should take a look at, or at least have an idea of their moments of inertia. Again, I think you should be able to put them in order from smallest moment of inertia to largest moment of inertia. Let's assume they all have the same radius and mass. The largest moment of inertia should be a ring because all the mass is located at the edge. So a ring has the largest moment of inertia. The next one would be the hollow ball. Because it's hollow, most of the mass is on the edge, but not all of it. The next one is a disk. It's got all that mass spread out. And a solid ball of these has the smallest. Because so much of the mass is located at the center. There are other shapes in the table. These really are the ones that get used on the tests the most. And those are the moments of inertia of the basic shapes. Now I have one last thing about moments of inertia I want to tell you about. All right, let's say I have a solid cylinder. You don't need a new shape to describe a solid cylinder. If the solid cylinder is going to be rolled like a rolling pin through its center, you would just use a disc to describe it. You have to look at the way the object's rolling. And if it's going to roll in such a way that there's already a shape that describes how far away the mass is from the axis, then just because it's thicker and not super thin doesn't change the moment of inertia. Like a door, we would use a bar rotated about its end. A rolling pin, we'd use a cylinder rotated about its middle. But, and this is something I did not say on Friday, what if I decided to rotate it about an axis through its middle? If I try and do that, well, then from the side it's going to look like a bar rotated about its middle. So when you're considering these moments of inertia, it's based on which axis you are using. So if I rotate this one that way about its middle, suddenly this becomes a bar. Moments of inertia are about the shape, but they're mostly about where the axis of rotation is. All right, that's a rehash of everything on Friday. I need to add something today. Okay? Any questions? Yeah. Our goal here is to try and understand the way in which objects spin or turn or all that. Spinning is all around us in ways you might not fully appreciate, whether it be the engine of your car, opening a door, something as simple as the gears that operate inside your watch. All of these things that are spinning have moments of inertia. They all require torque to get them to start moving or torque to get them to stop. So there's a lot of places where this shows up. For us, we're going to look at the big picture of it. And it comes right back down to this concept of torque. And I want to remind you about force before we talk about torque, where the second law tended to be this really difficult thing where we had to draw a free body diagram and you had to figure out all the forces that were acting on the object and then what would happen. And it got built up in our heads too much. But this just says, if you push on something, that's this side, then its motion changes. That's all it is. Newton's second law is really pretty straightforward and simple. We had all these rules to figure out how to use it because there's lots of forces acting on it. But if you go to push on something, then you can change its motion. That means you can speed it up or slow it down or change its direction. That's what change motion means. Speed up, slow down, change direction. It could be all of those, it could be none of those. M represents how effective you'll be. This is inertia. Objects with less inertia, you can be more effective at changing their motion. Objects with more inertia, it's harder to change their motion. That was Newton's second law regarding moving an object from one place to another. You tend to build these things up into being more complicated than they are, but something can be moving and it doesn't require a force. But if you want to change its motion, then all of a sudden it does. That's what it comes down to. Torque is the same way. Except with torque, we have how to apply a torque. It's not just pushing an object. To apply a torque, I have to push on the object, and where I push on the object matters, and the angle I use to push on the object matters. So this whole side is how I apply the torque. So this is how what you physically do to get something to spin. You push on it with some force away from the axis of rotation. This could be where you grip a screwdriver or a wrench. It could be how you use the door handle. It could be how you spin a frisbee. All of these things that you're trying to get to spin require that you apply a torque. You are going to be pushing on the object some distance away from the axis of rotation. And there's more effective ways to do it and less effective ways. This tells you how to be effective. It tells you, make sure your force is far away from your axis of rotation. Use an angle that's perpendicular to the axis of rotation. Make sure it's 90 degrees. That gives you the most effective application of torque. But then there's the result. Then there's what happens. And if it's going to be like Newton's laws, it's going to have something that deals with its inertia and the change in motion. So it's not a surprise that torque equals two things. The inertia of the object, the rotational inertia, and how its motion changes. So when we look at torque, torque is broken up into parts. This side I say is the application, how you apply the torque, and this side is the result. What happens? All right, now we have not done an example like this yet, and this is what the rest of the chapter is all about. So that's what we need to do now. Questions so far about this piece? Now look at all the things that have to go into doing this right. Do you see all the possible places you can screw this up? And all the possible places that they can try and confuse you? If you want to know how a torque works, you might need to know the shape of the object. It's not just how massive the object is. It's not a box on the ground any longer. You have to know whether it's a bar or a disc or a ring or who knows what the heck it could be. It's not just how hard you push on the object. It's where you push on the object, what angle you push on the object. And the result's not going to be that it changes location. It could stay in place the whole time. Torque problems are a little more challenging, and they require a more careful consideration. So we're going to do 3 different problems. And some of them are going to be, I think, easy. Some are going to be hard. So the first one I'm going to do is space station problem. And normally I'd show video of this, but I'm trying to do this kind of in a hurry to give us time to work. So I'm not going to show video. But anybody ever seen 2001: A Space Odyssey? It doesn't happen that often that you find students who have seen it. It's the movie that has the scene with the ballet and the space station that's spinning. If I show a clip of it, you'll say, "Oh yeah, I remember that." But it's got this space station, and the space station has a little piece in the center. We're just going to look at the outside edge, this ring like that, and the ring spins. This concept of a spinning space station is pretty popular in science fiction because if you were to make a big space station and spin it, you could have artificial gravity. It was used in The Martian. If you saw The Martian, that's probably the most recent movie that has something like this, where there's a portion of the ship that's spinning so that the astronauts have artificial gravity. They don't really have gravity. What they have is, and I'm going to exaggerate the size of an astronaut, they have this part of the ship that's spinning. Their body wants to go this way to prevent them from going that way and enter space. There's got to be a force pushing them this way to keep them going in the circle. That is the centripetal acceleration acting on them. Together, you put these things together and you have a condition where it feels like you have gravity because you're using your own inertia and the spinning part of the ship to try and keep you firmly planted on the ground. Of course, the problem is that you have to spend the entire time walking on the inside of this circle. So it works. It provides artificial gravity. The downside is your entire space station or your entire spaceship has to be spinning the whole time. Well, that could work. It could. Anybody see Passengers? Okay. They effectively use this as part of their plot element with the spinning spacecraft. There were some issues with it. You know, they had the space station suddenly stop rotating. Like, that probably wouldn't happen. Once you get something spinning, it has inertia and stays spinning. There's a spectacular scene where the woman's swimming and can't get to the surface because all of a sudden there's no gravity. That would be dangerous. But for the most part, the idea of a spinning spacecraft is great. We have experimented with this in space. We have not built anything big enough where we've been able to have artificial gravity, though. We've just been doing experiments. And anybody who's been on a spinny ride knows you can experience this. So every roller coaster that goes upside down, you feel firmly planted in your seat the whole time because of this. Anybody who's ever had one of those rides where you're at the amusement park, we talked about these too, it spins kind of like this, has a little lever here on the ground, and then once this whole thing is spinning and you are all sitting in here like this. Anybody seen one of these? Yeah, the whole thing tips upwards like that. Now you're spinning, you know, oh wow, look, we're going up and down. This is fantastic. I can't wait to throw up. You know, one of those jobbies. Yeah, same idea. It uses the same principle, but this time we put you someplace to use it as artificial gravity. You know, we keep talking about this idea that humans are going to go to Mars someday and all that. This is just one piece. By the time you get to Mars, nobody will be able to stand up when they got out of the spacecraft. Without enough force on your bones, you begin to have bone loss. So the idea of creating artificial gravity is pretty important, or else all your astronauts turn into Wallies, I guess, and won't be able to stand up when they get there. They can fix this problem. This problem has been pretty well solved with this fake gravity thing. The other problem is that you're being irradiated by the sun the entire time. The Earth protects us. Spacecrafts don't. The International Space Station is inside the protection of the Earth, so it's okay. But the guys who went to the moon were not. So those couple of days they spent outside the Earth, they got irradiated the whole time. And it's like getting, you know, a constant X-ray the entire time you're outside the Earth's atmosphere. Outside the Van Allen belts. That has not been fixed yet. We don't have a way of shielding the astronauts yet. So if you're going to go to Mars, you're talking about 3 months on the way out there of nothing but pure irradiation from the sun. It's they've had some interesting options to try and fix that. All right, so we're going to find the acceleration now that we know that the final velocity is 1.26, and I just hit record. I don't know where I was before that, so if you ever watch this video, it might jump around quite a bit. Yay. So I see 4 pieces together there, with one being unknown. I think I can probably come up with a motion equation that has those things in it. So I'm thinking this one works best. You guys all on board? Awesome. So find alpha, which is going to be omega final minus omega initial over time, or 1.26 minus 0 over 20. Yay! This is really fun. All right, so line it up for me. What's alpha then? It's going to be a little tiny number because the acceleration is small. Because the space station is big. We don't want to break it. Yes, ma'am? 0.063 and our units will be radians per second squared. All right, so checkbox complete. We have found the acceleration of the system. All right, guys, motion equations, they're going to be used again. This is what we have to do with them. Unlike the first part of the semester, I'm not going to spend a lot of time trying to trick you with the motion equations. I don't have to, but we're going to use them. So be prepared to be able to use them in problems like this. Our next step, question B, find the torque necessary to spin up the spacecraft. We have the shape of the spacecraft and we have the acceleration of the spacecraft. So in that torque equation, which had two parts, the torque equation had R times F times sine of an angle, and it had I times alpha. If you're trying to figure out which side of this to use, you're going to have to carefully consider what you have. The right side, this side over here, deals with the shape of the object and what it does. The left side deals with forces and where they're applied. So we have the acceleration. That's just what we found from part A. That automatically tells me we're using this side. So now let's deal with the shape of the object. From your table, which shape works the best? All right, this is a ring. And it's a ring of mass 12,000 kilograms and radius 5 meters. So if I want to find the torque, I need the moment of inertia of a ring, which is mr squared, times the acceleration that I just found in part A. All right, so although the acceleration is really small, that's because this object is really big. 12,000 kilograms with a radius of 5, which will be squared, all times my itty-bitty acceleration, 0.063, and this will produce the required torque. That's going to be a big number-ish. Again, the number's not important to me. It's recognizing that this is the result side of our torque equation, and we're going to have to use the acceleration to get there. But at this point, you guys have done all the typety stuff, so you should be able to tell me a number. Go ahead.
189.00.
18900?
18,900.
All right, 18,900 units are important here. And I could prove to you that it's kilograms, meters per second squared times meters, but I don't feel like it. The unit of torque is the meter Newton. We put the meter on the outside first. Meter Newton. That's just convention. Aw, boy, I bet you're sad the bell rang. But before you walk out, please note that the last part is to find the application of the torque. Now that we know the size of it, I'm not going to bore you, but you are looking from the force from the engines. You already have the radius. And the angle will automatically be 90 degrees if you mount the engines on the edge. But before you walk out the door, how many engines are there? So you need to make sure you understand that there's actually 2 engines. Okay? Each one provides half the necessary torque. All right. Here